Okay, hello. So today we're going to be taking a look at combinatorial proofs. We'll go through one, maybe two examples, but we'll go through it at a very slow pace, and hopefully everything that I talk about will make full conceptual sense and will help you in the future with combinatorial proofs. So our first example is already written here. Disregard the fact that I have two microphones on. That's a different discussion. And we're asked to prove via combinatorial proof that 3 to the n equals this summation from k equals 0 to n of n choose k times 2 to the k. Before we jump into it, let's briefly talk about what combinatorial proofs are. So a combinatorial proof is a way of proving an identity. So prove identity, or in this case, like an equality. But there's a couple of steps to combinatorial proofs. Step 1 is to pose a counting question. So what this means is we're going to have some creativity involved. By looking at this problem, we're going to develop our own word problem, if you will. And so we're going to pose that as a counting question. And then the way we'll show this equality is by using the counting question to solve for the left-hand side. So meaning we pose some question, suppose Alice has 3 bananas and Bob has 2, blah, blah, blah. And we're going to now look at the question we just developed and come up with some sort of procedure of solving it such that our answer takes the form of the left-hand side. And then we're going to use the question again to solve for the right-hand side. And then we'll conclude, since we had the same question to start with, and we came up with 2 different looking solutions, since they answered the same counting question, they must be equal to each other. Because nothing changed within the counting question. So this is the very rough outline of what we're going to follow. So the question is, how do we develop a counting question? For this, it comes down to a couple of the things we've already learned about in the world of counting. For example, on the right-hand side here, we see a summation. And before I go any further, our counting question should in some way be influenced or inspired by this identity. Because we don't want to just come up with something random. We want to choose a question that will get us one of these answers. Which means one of these answers should be really easy to obtain from our counting question. Anyways, I digress. We see a summation here of many different things. In fact, it's the product of 2 quantities. But when you see summation, you start to think of addition, and with counting, when we add a bunch of things together to get an answer, usually they're like disjoint cases. So that might be something I start thinking about. 3 to the n is equal to 3 times 3 times 3 n times. So here I'm seeing multiplication. I might start to think about the multiplication rule. You know, having some sort of procedure that has n steps, and in each step it can be performed 3 ways, right? If I have that, then by multiplication rule, I'll get this quantity, 3 to the n. So this seems quite easier to work with. This right-hand side is a bit too complex for my liking, and I don't think I can really create a counting question based off of that. So, given this, 3 to the n is equal to that, 3 times 3, I want to develop like an n-step procedure where each thing has 3 possibilities of occurring. So, I don't really have any tips of coming up with this question other than using whatever you've figured out thus far and really thinking about like what kind of question would have such an answer. And then just, go through trial and error. It'll take some practice, some getting used to, but eventually you'll get the hang of it. So here's a question that might work out. So here's an example of a question that I came up with. Suppose I have n distinct pegs that I want to paint. Each peg can be colored, I should say painted, red, blue, or green. How many ways can I color my pegs? And you might be thinking, why would you be painting your pegs? Well, that's just something I happen to do every single Saturday evening, so don't question it. So here's my question. So that's step one. Now I want to be able to solve the left-hand side and the right-hand side. In other words, I need to solve this question twice, not just once. So I'm sort of just going to ignore this, that I was asked to do all of this, instead focus my attention to this question, but in the back of my mind, I'm thinking, I want to solve this question so my answer looks like that, or I want to solve it so it looks like that. So let's do it. So we're going to solve the left-hand side. Well, what is one way of solving this? You know, maybe I have these pegs that are written out for me. And I have my colors to choose from. Well, one way of counting how many ways I could paint or color them is to look at the first peg and assign it a color, maybe blue. Then look at the second peg and assign it a color, any one of these colors. I don't know, maybe green. And so on and so forth. And then within each, what I'll do is like figure out how many ways each of these steps could be performed and multiply them all together. This is severely influenced by what I talked about earlier, which helped pose this question. So if we were to write this out more formally, the way I can count how many ways I can paint my pegs is by following a procedure. So step one, I'll color the first peg. In step two, I'll color the second peg, all the way up to the nth step, where I will color the nth peg. And so the procedure is as such, because no matter how I can paint these pegs, like whatever this is, or blue, green, whatever, any sort of coloring can always be obtained by this procedure. I.e., I can get this peg to be red by, in my first step, if I chose the color red to color it. And here I could have chose blue to color it. So every single coloring will be obtained by this procedure. Now it's just a matter of figuring out how many ways can I perform this procedure. Well, my first step, I have 3 options for the color. So there are 3 ways I can perform this step. Here, for the second peg, I again have 3 colors to choose from. And that proceeds for all of the steps, up to the nth peg, where I also have 3 ways. You know, I can use any of these colors. Using the multiplication rule, since each of these values is a constant, we can say that there are 3 to the n ways to paint my pegs. And so what I've done is I've solved my counting question. I've come up with an answer to this question. And it just so happens that my answer is the left-hand side. But this is only part of the combo proof. Now I have to re-solve this question, perhaps perform a different procedure such that my final answer looks of this form on the right-hand side. And that's a little bit trickier. Okay, so with the left-hand side, things were pretty easy because we had used the left-hand side to inspire our question, and then when we solved this question, we sort of did some like reverse engineering to get the value that we thought of originally. We again have to solve this counting question, and we want to keep in mind that this is the answer we want to obtain. The procedure for the left-hand side was arguably the most natural procedure to solve this question, but now when we have to move into the world of unnatural solutions, we have to be careful such that the procedure we choose will get us this answer. Otherwise, we're going to waste time getting a different expression. So how do you come up with a procedure? This is incredibly daunting, right? Looking at a summation where we're summing on the product of two terms. Here is where you have to use both your skills of counting and the principles of counting that you know, but also a little bit of creativity and pattern matching per se. What I mean by this is if we were to just ignore all of the math involved and come to this question and be like, how many ways can I paint it? In the first procedure, I sort of treated all paints at once. And I went peg by peg. I said, you know, this can be red, and then for the next one, it could be any of the three paint colors. And then I was doing all three paintings at once. What's another way I could paint my pegs? Maybe I didn't have all three colors of paint available to me immediately. Maybe they were coming in the mail, and maybe I only had red paint to start with. So maybe I would figure out which pegs I wanted to paint red, and then I would paint them red. And then the next day, the green paint would come, and then I would be like, okay, out of the remaining unpainted pegs, which ones do I want to color green? So I would choose those, and then color those greens. And then finally the blue paint would come, and I'd be like, well, okay, all of these paints that are left over are uncolored because everything else is red or green, so I'll just paint those blue. This is like a little bit of creativity. The order in which the paint arrives to me doesn't matter. I can still paint it however I want. It's just in this way, I don't have the paint available to me. So perhaps that would give me a different solution. But here we should be a little bit careful and look at what we're summing. If I were to read this out loud, it's the sum from k equals 0 to n of n choose k times 2 to the k. N is the amount of pegs as mentioned in our question. So we are choosing potentially k of the pegs, kind of just me spitballing, and then 2 to the k, that's similar to 3 to the n, so maybe it's some sort of procedure where there's two options for each of the k pegs we just selected earlier. Is that starting to make sense? Right? Like I have n pegs, maybe I should choose k of them for some reason, whatever that reason may be, and then on those k pegs I'll do something such that there's two options for each peg. So the idea I presented where the paint kind of came in the mail, maybe I'm sort of on the right track. Maybe I only have two colors of paint available to me. And that I can use to paint k of my pegs. But what's k? Well, maybe k would be, you know, the amount of pegs that I want to color either red or blue. Maybe that's the only two paint colors I have with me. K could be any number. I could want to paint 0 of my pegs red or blue. Maybe I would want to paint 1 of them red or blue. Maybe I wanted to paint all n of them red or blue. To account for all of those possibilities, we will consider every value of k that it could be, and then sum on that. We're breaking it up into disjoint cases. Let us write this out properly. So we'll ignore the color green altogether. We'll worry about that later. Suppose we knew that I have my pegs, I want k of them. I don't know, like, k is just some integer, but I want k of them to be red or blue. How many ways can we do such a painting? Well then, in step 1, I will choose which k pegs I want to paint. So thus far, we'll have to do it here because I don't have that much room. thus far, I've looked at my n pegs, and I've chosen which ones of them I want to paint red or blue. So maybe it's this one, maybe it's that one, maybe it's that one, maybe it's that one. Maybe it's this one, this one, this one, and this one, right? We're just choosing which ones of them to paint. Now we have to actually paint them. So we'll focus in on those K pegs. So really, step 2 will be paint the K pegs red or blue. And so, okay, so we'll keep that there for now. So we've chosen our pegs. I'll erase this example for now. And maybe this one is colored in red, maybe this one's colored in blue. Let's just draw another one here that didn't get chosen. But maybe this one was colored in red and this one was colored in red. So I've colored some of my pegs, but not all of them. In step 3, all of the remaining pegs, these are the ones that I did not want to color red or blue. Because at the start I said, I know for certain K of the pegs, they must be red or blue. Anything else I don't care about. All of the other pegs must be painted with the remaining color we haven't used. So we will paint the remaining uncolored pegs green. So for some value of K, I know exactly how I can paint those pegs, such that K of them are red or blue. I should write that here. Okay, well, how many ways can I perform each step? This one, there's n total pegs, and I'm choosing K of them to be red or blue. So this can be performed in n choose K ways. I'll sort of box that, I kind of ran out of room. Step 2, I'm looking at the K pegs and painting them red or blue. So this can be decomposed into smaller steps. This would be paint the first of the K red or blue. And then 2B would be the second of the K red or blue. And then so on to step 2. Letters are annoying because it's not going to be K, it's going to be some value. I'll just call it alpha, where we'll paint the Kth red or blue. Each of these steps can be performed in 2 ways because it's either red or blue. We're doing it K times, first, second, third, all the way up to Kth. So we get 2 to the power of K for this step. Lastly, I just have a bunch of uncolored pegs, and they must be painted green. There's no other way I can do it than just by painting them green. That's all I can do. So this can only be performed in one way. So when I know the value of K, then the amount of ways to perform, the amount of ways we can paint K of our pegs red or blue is n choose K times 2 to the K. However, this was just for a fixed value of K. I said I knew K of them I want to paint red or blue. But K could be any value. I could have said I want 1 of mine to be painted red or blue. I could want 100 of them to be painted red or blue. I could want all n of them to be painted red or blue. To account for all of those possibilities, we would have to do these steps for all values of K, which introduces this summation right here. For K equals 0, 0 of my pegs red or blue, there are that many ways to do it. For 1 of my pegs red or blue, there are that many ways to do it. We are going over all values of K and adding them together. We can do it because they are disjoint cases. Why are they disjoint? Because the number of red or blue pegs are different. So we can add them all up. I apologize, this last little bit of like this summation is a bit hand-wavy on my end, but that's for two reasons. Number one, I ran out of room, and number two, it would take a lot of time to write it all out, but hopefully verbally explaining it should give you an indicator of why this is true. But again, we have solved this counting question in just a different fashion. It gave us different values, but this is an answer to the problem. We have achieved this summation as an answer to this question. So we have shown this expression also answers the same question. Since we have the same question and we came up with two separate solutions, they must be equal to each other. I know at the start I said I might do one or two examples. I think I will just stick with one here, just to not make this too long. And also the second example I had prepared is, won't necessarily teach anything new, but there are a few things that I want to point out in conclusion of this video. First of all, the counting question you develop should be minorly influenced by the equality at hand. I came up with this question because I knew I wanted to have 3 options for all n of my objects, because that would get me the left-hand side. So I was minorly influenced by this left-hand side. Second of all, know your counting properties. I used multiplication rule to get this side right here, and I knew what kind of multiplication rule, what kind of procedure I would want to get that. Similarly here, I knew I wanted to add disjoint cases, which influenced how I solved the second side. Third of all, like for this, n choose k, again, we dealt with distinct stuff, we were choosing some of them and then applying a smaller operation on there. So you have to be creative in how you're solving these questions. It's not always going to be natural, but think a little bit about how you could do things a little bit differently. And the way I explained about, maybe I didn't have all paint available to me at once, that is a good way to get you on the right track. And that's in fact how we got the right-hand side. I'll admit, I'm really bad at combinatorial proofs. These are like my least favorite thing in proof techniques. However, they are very, very creative, and they rely a lot on your understanding of how, numbers work together. It takes some practice, but with these small observations of how things can be put together, you'll be able to solve a lot of combinatorial proofs. Sometimes they take long to solve. You're just gonna have to work through it. That's the best advice I can give. Hopefully this explanation was helpful to you. And yeah, thank you for watching.